So let's see, let's go back to where we were at the end of last week. We were talking about cardiac and smooth muscle. Here's a cartoon that I used to talk about cardiac muscle. The key points are calcium-induced calcium release. That is to say, calcium influx through voltage-gated calcium channels in the calcium influx through voltage-gated calcium channels in the T-tubular membrane. That calcium influx triggers calcium release from the SR. Those two sources of calcium bind to troponin in cardiac muscle. Just for your information, this is not a key number, but about 90% of the calcium that is responsible for contraction in cardiac cells comes from the SR. Only about 10% of it comes from the voltage-gated calcium. The key point is calcium-induced calcium release, cytoplasmic calcium increases, calcium binds to troponin, troponin conformational change, cross-bridge cycling, contraction. This is getting at one of the problem set questions where more calcium causes more contraction by moving more troponin out of the way. More troponin is occupied by more calcium, more conformational change of the troponin, more cross bridges can form, stronger, faster contraction. That's cardiac muscle, and we'll be talking more about that today. Smooth muscle is the one that doesn't use troponin. The calcium sensor, so it doesn't have T-tubules. It doesn't have a robust calcium-induced calcium release. The calcium sensor is calmodulin, not troponin. Calmodulin binds the calcium, causes conformational change to calmodulin. Calmodulin activates a kinase, myosin light chain kinase. Myosin light chain kinase phosphorylates myosin. The name tells you myosin light chain kinase. Myosin kinase tells you that it phosphorylates myosin, and that phosphorylation of myosin is what causes contraction, cross-bridge cycling, and contraction in smooth muscle. Similarities: more calcium, more calmodulin activation, more myosin light chain kinase activation, more cross-bridge cycling. So that's a similarity. But the source of the calcium is different. Calcium can come from G2 coupled receptors and the downstream effects releasing calcium from ER, SR in smooth muscle. And the calcium can come from voltage-gated calcium channels in the surface membrane. But there is not the robust calcium-induced calcium release in smooth muscle the way there is in cardiac muscle. So that's another difference between smooth and cardiac muscle. So let's see, let's just go through the problem set real briefly. The first question was asking you to put these things in order for the GQ story. Most of you did just fine on that. Some of you missed a couple of things and lost a few points. I'm happy to go through the questions if you have a specific one, but I'm not going to go through the order of things because you know that. I mean, you showed you that you know that. The proteins, well, let's go through them. The receptor is a protein. GQ is a protein, especially the alpha subunit of GQ undergoes a conformational change. Beta gamma complex, not so much, but I accepted it. Calmodulin is a protein that undergoes a conformational change. Phospholipase C is a protein. Protein kinase C is a protein. Calcium release channels are proteins. And the enzymes that are phosphorylated by protein kinase C and activated by calmodulin are all proteins that undergo conformational changes. So many of you missed enzymes as a protein in this story that undergo conformational changes. That was a common mistake, the misenzymes. Most of you got the rest of them. PIP2 is not a protein. IP3 is not a protein. Diacylglycerol is not a protein. Okay, and then question 3 was asking you to go through, use the same thing to basically tell me the story of the GS signaling pathway. The one mistake that many of you made was to forget to say that cyclic AMP diffuses. That was a common mistake. That's a key point because that's one of the key functions of a second messenger. So I was looking for that. And I took off a point if you forgot to say that cyclic AMP diffuses before it binds to pKa. Strictly speaking, cyclic AMP binds to the regulatory subunits of pKa, but I didn't add or subtract points for that detail. The question 4 about digoxin. Most of you got this right. The key concept here is that by inhibiting the sodium pump, you inhibit the sodium gradient. The sodium gradient is the source of energy for the sodium-calcium exchanger. So by inhibiting the gradient, you inhibit the source of energy for the exchanger, so less calcium is pumped out by the exchanger, so calcium goes up. The next one is that I was just asking you to tell me that calcium binds to troponin, and basically tell me this story. I didn't ask you to, I mean, this question didn't specifically ask you to go through the cross-bridge cycle. I was happy if you did it, but I didn't take off points if you didn't. I was basically looking for troponin, conformational change, myosin binding sites are exposed on actin, cross-bridge cycle. Question 5, the correct answer is depolarization. Most of you got this right. The idea is that if there's elevated potassium on the outside, there's less of a potassium gradient because the potassium concentration is high inside and low outside. If you went so far as to say the potassium concentration is so high on the outside that potassium is flowing in, you're dead. And I took off a point. I mean, if the potassium goes that high, you are dead. And that, I took off a point for that. But the point is, even if potassium goes high a little bit, what there is decreased potassium efflux. We're not talking about net potassium influx, then you're dead. But there's decreased potassium efflux, that would lead to a depolarization. So that was the concept I was looking for. The graded, question 6, when I was looking for graded, basically I was looking for, in question 6a, I was basically looking for anything that told me that calcium is controlled, right? So more calcium channels, more open calcium channels, more calcium release, more contraction. Or you could go to the circa story. More circa, more calcium pumping, less calcium, less contraction. Any of that. I was just looking for basically your understanding that if we control calcium, we control, if we modulate, if we grade the calcium level, we grade the level of contraction. It's not all or none. And so that was sort of the total question of 6A and B. We can grade the calcium, and then grading calcium grades contraction. That's what I was looking for. And finally, on question 6, so what was the point of question 6? Anybody want to read my mind? Question 6 was the one about normal blood flow, and I was asking for how fast is blood moving in the aorta. And why did I ask you to go through this exercise? Okay, you don't have to read my mind, I'll tell you. The main point is to realize that physiology uses mathematics too. I was just asking you to use some simple geometry and some simple algebra. and so it's not just chemistry and physics, biology uses it too, so that was a point. The other point is if you did the calculation right, what you realized is that the flow rate of blood in the aorta is fast. And so the blood flows from the aorta to the end of the aorta, its entire 37 centimeters in 1 to 2 seconds. I accepted a lot of correct answers because it depended on what you used for the diameter of the aorta. If you used 3 centimeters, you got one answer. If you used 2 centimeters, which is what I used, and my answers are up on Moodle, you get a different answer. They're all okay. If you use 5 centimeters for the aorta, I think I took a point off because that's aortic aneurysm, and that's not normal. I accepted a lot of correct answers. So the point is, it takes about 1 to 2 seconds for blood to get from your heart to the end of the aorta. It's moving fast. And then in question C and D, I was asking you to realize that if that blood is now going not through the aorta, but through the entire systemic capillary bed, which has a 3,000 square centimeter total cross-sectional area, the blood is moving very slowly. And this is key, because the blood is moving very slowly through the capillary bed, both in the pulmonary capillary bed and in the systemic capillary beds, so that gas exchange can happen and nutrient exchange can happen. The blood has to flow slowly through the capillary in order for that diffusion of and exchange to happen. And so it takes about as long for the blood to go through the aorta, 1.5 seconds, as it takes the blood to go through a microcirculation capillary, 2 to 3 seconds, because the blood is moving so slowly. A couple of you actually didn't use the 3,000 square centimeter total cross-sectional area that I gave you. You actually, I forget who did this, but you actually calculated the diameter of a microcirculation and then multiplied that by 10 billion or something in order to get the number of capillaries. And you came up with a number that was pretty close to right. So. Are there questions about the problem set? Most of you did real well, and so the idea here is to reinforce your understanding through working with problems. Okay, so let's go on to start talking about the heartbeat. Now we're really getting into cardiac anatomy and physiology, cardiac A and B. We will transition to vascular A and B pretty soon, but right now we're going to focus on the heart. We can't only focus on the heart. The vasculature is an important part of the cardiovascular system, but right now we're focusing on the heart. And you've learned some of these names. In the past, I've whited out all of these names and used the laser to ask you to name things, but let's just go through this together. Systemic blood flow, systemic blood returns from the body to the heart via the inferior and superior vena cava. Enters the right atrium. And during diastole, when the heart is relaxed and that blood is returning, diastole, this is a key word. Diastole. Someone says diastole, I'll correct you. It's not diastole, it's diastole. During diastole, which is the relaxed period of the heartbeat, blood is returning. Blood returns to the right atrium, and it flows through the tricuspid valve, which is open during diastole. Into the right ventricle. At the same time, so now I'm moving in space, but I'm not moving in time. At the same time, blood during diastole, blood is returning from the lungs to the left atrium and is flowing through the bicuspid valve, which is also open. So systemic blood is returning to the right atrium and right ventricle, and oxygenated blood from the lungs is returning through the pulmonary veins into the left atrium and into the left ventricle. That's diastole. Blood return, filling of the ventricles through open tricuspid and bicuspid valves. Then the heart triggers itself to beat. We'll talk about we're going to within a half an hour. We'll talk about the trigger for heartbeat. But let's just say, okay, the heart triggers to beat, and and the ventricles contract. So now we are talking about systole. Systole is the contracted, or really contracting state of the heart. The ventricles contract. On the right side, the blood that's in the ventricles now is squeezed, and that closes the tricuspid tricuspid valve closes because of that pressure that is built up but because of the contraction, and the bicuspid valve closes. So the blood doesn't regurgitate from the ventricles into the atria. The pressure is going to build up so much that it's going to flow out on the right side, it's going to flow out into the pulmonary artery. So what's going to happen is the pressure is going to open the pulmonary semilunar opens. And the aortic semilunar valve opens. Yes?
Is the aortic, is that on the left side?
The aortic is on the aorta, so that's on the left side. Yep.
Okay.
So this is the pulmonary semilunar valve right here between the right ventricle and the pulmonary artery. And this is the aortic semilunar valve between the left ventricle and the aorta. These valves open and blood is forced out from the ventricle into the pulmonary artery, from the ventricle into the aorta. Let me say that again. From the right ventricle into the pulmonary artery, from the left ventricle into the aorta. That's blood flow. Blood flows from the right side to the lungs, blood flows from the left side to the body. The closure of the tricuspid and bicuspid valve is the first heart sound. And then when we go back to diastole, so I'm circling back here, the semilunar, so at the end of diastole, the heart starts to relax again. The heartbeat is now terminating, starting to relax. The semilunar valves close. The tricuspid and bicuspid valves open, and this is the second heart sound. So what I'm doing is I'm walking through the heartbeat once. I will walk through this heartbeat 2 or 3 times over the course of the next couple of classes. So you'll see it. Right now we're getting the overview of the heartbeat. Then we're going to talk about it in more detail, and then we'll talk about it in more detail again. One more anatomical detail that you saw in the lab. Pericardium is that tough membrane on the outside of the heart. I'm not asking you to learn about the epicardium and the endocardium, so don't worry about those. Myocardium is just the name of the muscles of the heart. Myo just means muscle, cardium means heart muscle. The septum is Latin for wall, I think. The septum is the wall between the two ventricles or between the two atria. So we have an atrial septum and we have a ventricular septum, or an interventricular septum. Septum is just what separates the two ventricles. And you saw in lab last week papillary muscle and chordae tendineae, which are important for preventing the tricuspid and bicuspid valves from getting blown out by the pressure being generated in the ventricles. Okay, so what I'd like to do is, so I've walked through it. Let me show a video. So this is just a story, but with some animation that helps solidify what I just said.
The normal heart has two sides, a right side and a left side, and four chambers, the top receiving chambers, or atrium, and the lower chambers, which are thick-walled pumping chambers, called ventricles. Red blood cell will come from either the superior vena cava or the inferior vena cava and enter into the right atrium. The blood then flows across the tricuspid valve to the right ventricle. The right ventricle then squeezes and ejects that blood cell into a vessel called the pulmonary artery. Pulmonary artery splits into two vessels, each going to the lungs. As that red blood cell makes its way through the lung, it returns through the pulmonary veins to the left atrium. That blood is now oxygenated. It's picked up oxygen, then goes across the mitral valve into the left ventricle, which does most of the work in terms of delivery of blood flow to the body. That blood cell is now ejected into the aorta to some organ or muscle or skin in the human body.
Okay, so that goes through it real fast, but this link is available to you on, from the, that link is available to you because the link is pasted into the PowerPoint. So all you gotta do is go to the PowerPoint, cut and paste the link, and you can watch that as many times as you want. Are there questions about this overview of the heartbeat and the movement of blood? Okay, so now I have to talk about the thing that paces the heart, right? The heart beats once a second or so for your whole life. And it's modulated by the nervous system, but it doesn't depend on the nervous system for the heartbeat. It has an intrinsic pacemaker. So this is different from breathing. And so if you can hold your breath, and then at a certain point you can't. You can't stop your heart from beating. You don't have that power. Your brain doesn't have that power. You can make your heart beat faster. You can make your heart beat slower. If you're into meditation, if you go into a meditative state, your heartbeat will slow. If you're into exercise and you go exercise, your heart will beat faster. So you can control it, you can modulate your heartbeat, but you can't stop it, and you can't start it. It's got an intrinsic pacemaker. And you could figure this out, right? We can do heart transplants. And when we transplant a heart from one person to another, we connect the plumbing, we connect all the tubes that move blood, but we don't connect the wiring. A transplanted heart isn't innervated the way a normal heart is. So let's talk about this pacemaker mechanism. We want to talk about how the heart controls its pace. And in order to do that, we have to talk about electrical activity, we have to talk about ion channels, and we have to talk about the pattern of electricity movement through the heart. So the key anatomical phrases are here. The sinoatrial node, the sinoatrial node, or the SA node, is the pacemaker, is the normal pacemaker. Those are cells that are specialized for controlling the rate of the heart. Electrical information, so the sinoatrial node fires an action potential. That's pacemaking, fires an action potential. And those action potentials spread throughout the atria. Why do they spread throughout the atria? Remember, all those cells are connected by gap junctions. So an action potential in the sinoatrial node gets communicated throughout the atria by cell to cell to cell communication. And the atria contract, and that's called atrial systole. Why did the cells contract? Well, they just fired an action potential, depolarization of the T tubule, depolarization of the voltage-gated calcium channel, calcium-induced calcium release. Now we're off and running to contraction. Then there is a layer of insulation. So the atria are generally insulated from the ventricles. So the electrically insulated. So the action potentials can't just move straight from the atria to the ventricles, except at another structure called the atrioventricular node. So the atrioventricular node is the window, the electrical window that allows electrical information to go from the atria into the ventricles. If there is a breach in this electrical insulation, that would lead to an arrhythmia or a dysrhythmia, an abnormal beat. And we'll get into that later. But let's stay focused on normal. So normally, the electrical information goes through the atria, atrial systole, atrial contraction, atrial systole, and then the electricity, the spread of action potentials goes through the AV node into this structure called the bundle of His. It's not his. Hers, women have it too. It's the bundle. His is the name of some anatomist. Czech anatomist, I think. Bundle of His. And I'm not even sure I'm saying that right, but I just want, it's not his. So, from the AV node into the bundle of His, into the bundle branches, the bundle of His branches into the bundle branches, and then into the structure called Purkinje fibers. Purkinje fibers. So now the action potentials are being delivered throughout the ventricles. And we get ventricular systole. Again, action potentials, depolarization of the T tubule, depolarization of the voltage-gated calcium channel, calcium-induced calcium release, contraction. So the bundles and the Purkinje fibers are specialized for taking those action potentials throughout the ventricular muscle fast, so that the ventricular muscle contracts as a unit. We don't want one part of the ventricle to contract much before another part. There's a little bit of a difference, and we'll get into that when we get into the electrocardiogram on Thursday. But generally, overview, the atria contract as a unit, and then the ventricles contract as a unit. The delay between atrial systole and ventricular systole is important. There's a delay, and the delay is due to the AV node. So the SA node is the pacemaker, and the AV node is the delay maker between atrial systole and ventricular systole. Is that clear? We'll get into the mechanisms of that pacemaking and that delay in a few minutes.
Sorry, can you just repeat that?
Sure. The SA node is the normal pacemaker, and the AV node creates the delay between atrial systole and ventricular systole. And that delay is about a half a second.
Thank you.
So let's now get into, well, the next slide shows, let me clean this up. This slide shows the story in some snapshots. So, let me just walk through it. SA node, fires action potentials. Action potentials spread throughout the atria. That's this yellow cloud moving through the atria. Atrial system. You can't see it, but it's contracting because action potentials have happened there. Moving through the AV node, moving slowly through the AV node, moving through the bundles and through the interventricular septum. Spreading throughout the ventricles, very fast because of the Purkinje fiber network. Ventricular systole. Then it's over. You gotta have another heartbeat, so you've gotta relax so that you can refill. And so we go from a contracted state back to the relaxed, beginning state. State over here. Okay, so that's the heartbeat. We'll talk about the electrocardiogram on Thursday. In fact, you're going to measure electrocardiograms in lab on Thursday. Okay, questions? So remember, you just remember that the reason that the action potentials move from cell to cell to cell is the gap junctions. Here's a slide to remind you that one cell is connected to another cell through channels called gap junction channels that go all the way from through one membrane and through the other membrane. So these are channels that go through two membranes that are very closely connected to each other at the desmosomes. So let's talk about the molecular mechanisms of pacemaking. So I like to get into the molecular mechanisms, right? I teach anatomy, gross anatomy, but then I like to get into the cellular anatomy, and I teach physiology, and when I teach physiology, I like to get into molecules. So now we're going to talk about the molecular mechanism for pacemaking. So a pacemaker cell, overall, a pacemaker cell spontaneously depolarizes, spontaneously fires an action potential, repolarizes, and does it again, over and over and over again, about once per second for your whole life, right? So this is a cartoon of the action potentials in a typical SA nodal cell, a pacemaker cell. So let's review. Why is there's no such thing really as a resting membrane potential because it's never at rest. It's always depolarizing or firing an action potential. So we can't really talk about resting membrane potential. But let's go to this one point here. Why is this point negative? I'll give you a hint. It's the same mechanism as why a typical cell has a negative resting membrane potential. Why is this point negative? Potassium channels, right. So here we have well, let me go. So this is, we call this the maximum diastolic potential. Maximum, the most negative diastolic because it's at rest potential. And it's negative because for the same reason that the resting membrane potential is negative. Potassium channels. Potassium flowing out, making the inside of the cell negative. Now we get to a specialization. Pacemaker cells are specialized, unlike cells that have a resting membrane potential, right? These cells don't have a resting membrane potential. They don't rest. They're constantly in movement, or the membrane potential is constantly moving one way or the other. These cells have a set of channels called IH. What does IH mean? I just stands for current. It's a biophysicist's letter for current. H stands for hyperpolarization. So these are hyperpolarization activated sodium channels. Your book calls them IF, which is an old-fashioned name. It's the same thing. F stood for funny. They aren't funny at all. They're weird because they are activated. So they're activated by hyperpolarization. So when they were first discovered, somebody said, that's funny, and they called them the funny channel. But it's not humorous, and it's not really that weird. They're activated by hyperpolarization. And so the better name is IH. If you use IF, I'm okay with it because your book does. IH channels are hyperpolarization activated sodium channels. They are expressed in pacemaker cells. They are not expressed in most cells. So the hyperpolarization caused by the potassium channels that brought the membrane potential down here, negative, opens both hyperpolarization activated sodium channels. Which way does sodium flow? Sodium flows in. What does that do to the membrane potential? Depolarizes it. So the hyperpolarization activated sodium channels cause a slow depolarization. Why is it slow? It's slow because their kinetics is slow and because there aren't very many of them. They're expressed, but they're not expressed in high numbers.
They're channels or?
They are channels.
Or no, so it's not, the channels aren't expressed?
The channels are not expressed in high numbers. They are certainly expressed, but they aren't, it's not like the voltage-gated sodium channels that are expressed in high, the ones that cause depolarization are almost always expressed in very high numbers. So these are expressed in, they're expressed, but they're not expressed, in abundance. And so there's a dribble of sodium in, and that causes a dribble of depolarization. That dribble of depolarization opens voltage-gated calcium channels. The L-type calcium channels. Your book also talks about a T-type calcium channel, which I'm not going to ask you to learn about, but it's just another type of calcium channel. So the depolarization that was caused by IH now opens voltage-gated, depolarization-gated calcium channels. Which way does calcium flow? Calcium flows in. That contributes to this slow depolarization. Okay? That's the slow depolarization phase. Now the membrane potential has gotten it's gotten high enough that we open a lot of voltage-gated calcium channels. So here, this was a small depolarization. It opened a few voltage-gated calcium channels, but eventually the depolarization gets big enough that it opens a lot of calcium channels. So a few, a lot. We go from a slow depolarization to a fast depolarization. Now this is an action potential, and calcium is flowing in. And these pacemaker cells are contracting, but we don't care about their contraction. That's not their job. Their job is pacemaking. But it's firing an action potential. What's different about this action potential from every other action potential that you've learned about so far? In all the other action potentials you learned about, what was responsible for the depolarization of the action potential? Voltage-gated sodium channels. In these pacemaker cells, voltage-gated sodium channels don't play a role. It's voltage-gated calcium channels that play the role of sodium channels in causing the action potential. And because voltage-gated calcium channels are slow relative to voltage-gated sodium channels, the depolarization is relatively slow. It's not as fast as you'll see in a second. So, slow depolarization becomes a fast depolarization because we go from a few voltage-gated calcium channels to a lot of voltage-gated calcium channels.
And what is it that
What causes
causes it to
the
go from slow-
enough depolarization? We get to a threshold, a set depolarization, where we go from a few to many. Remember, voltage-gated calcium channels are open by depolarization. So the greater the depolarization, the more open they are. And we just go from a few to a many. And there's probably no, it's probably a curve here, right? Because it's a continuum, it's not an angle. Eventually, the voltage-gated calcium channels, what happens after a voltage-gated channel opens and ions flow? What's the next step in voltage-gated sodium channels and voltage-gated calcium channels? Inactivation. Voltage-gated calcium channels inactivate. And what else happens? Say again?
potassium channel?
Voltage-gated potassium channels, voltage-gated K channels, open. Which way is potassium flowing through voltage-gated K channels? Out. Potassium is flowing out because the potassium concentration inside the cell is higher than outside. Potassium flows out, which is causing a repolarization. So the repolarization is just like you learned about in the nerve. Voltage-gated potassium channels open, potassium flows out, repolarization until we get, and then when they repolarize, the voltage-gated potassium channels close because they were opened by depolarization and they're closed by hyperpolarization. Resting, I'm putting it in quotes here, resting K channels are open. And we get to a maximum polarization, which is where we start. Everybody clear why I'm saying resting in quotes here, where I usually am not so equivocal? Because there is no resting membrane potential, but those channels are still here.
Okay, just so I understand this correctly, so you start, you have a slow depolarization, then it goes to a faster depolarization, and then,
This is the action potential.
yeah, then you fire an action potential, then it starts to repolarize?
Yes, so voltage gated calcium channels that were open during the depolarization inactivate. Voltage gated potassium channels that were opened by this large depolarization open. Potassium flows in. The calcium is getting mopped up by pumps. Let's not worry about that. The potassium is flowing in, and the potassium, I'm sorry, I said it wrong. Potassium is flowing out, and that causes repolarization.
Okay, and then at the bottom, that's a hyperpolarization.
We would call this a hyperpolarization. It's a little tricky because if you can't define a resting membrane potential, you can't really define a hyperpolarization, but we call it a hyperpolarization anyway.
So are those resting K channel the same as voltage?
No, these are not voltage gated. So the voltage gated potassium channels and the resting potassium channels are two different types of potassium channels.
And when the resting K channel is open, K flows in?
Nope. K always flows out. Okay, so here we have a little bit of K flowing out because we only have the resting K channels open. And here we have a lot of K flowing out because we have both types of channels open. John?
Are the resting K channels open during the entire action potential?
Kind of, sort of. I don't want to lie to you and say yes, because they are open, but they are blocked by intracellular ions, and so there's very limited potassium flowing out through resting K channels here. It's a detail.
What happens to IA channels during the
So that's a good question. So if they're opened by hyperpolarization, what do you suppose happens to them here and here? They're closed. So they're open here, close, 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 start to open, 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 open. They're opened during by strong polarization, hyperpolarization. So if you can, this is understanding these channels and how they do this is essential for understanding pacemaking in the heart. And it's going to become critical for understanding how the nervous system controls pacemaking, right? And you want to know that. You want to know why when you exercise does your heart beat faster? Why when you're nervous about your upcoming A&P exam or whatever, it's not that upcoming, but why when you have a problem set due, or you have a quiz that's due this weekend. I can make your heart beat a little faster. You have a quiz due this weekend. How did your brain tell your heart to beat a little faster? You need to know this mechanism. But the questions, they're really good because it helps me make sure that you and I are working with the same, information, talking the same language. Any questions?
So how does it change? I get the cycle of it, but how does that get faster?
Okay, we're going to talk about that in another class. I don't want to get ahead of myself. We will talk about that, maybe on Thursday, maybe not until next Tuesday. It's changing the activity of the channels.
So the IH channel will be closed till the calcium channel is calcium voltage channel is inactivated, or will be closed when the membrane potential, I don't know, reach.
Yeah, I mean, you should just think that if the membrane potential goes below -50, IH channels open. If the membrane potential is above -50, they tend to be closed. It's not an all or none thing, but IH channels are open below -50 and they close above -50. So IH channels are open, but now they start to close because we're getting above -50, but we continue to get the slow depolarization because now we've got the calcium flowing in, not the sodium flowing in. Okay, let's take a short break now, and because what I'm going to do is use this information and understand the action potential of contractile cells. Remember, we've been talking about pacemaker cells, but we also have to talk about the muscle cells that do the work of pumping blood. Those are the contractile cells, and we can go through this one pretty quick. Let's take a short break. Just for a minute. The quiz is due on Sunday at 11:30. At the CST desk. You'll pick it up from the CST desk when you're ready to take it. No, back up. You will decide you're ready to take it. You'll put all your notes and books and electronics away, far away from you, preferably. Then you will go to the CST desk and pick up the quiz and take it right there in CST. Do not take it home. Take it somewhere in this building. And then you turn it in. They generally take about 30 to 45 minutes. But there's no time limit. They clock them in and clock them out, but I don't look at that really. So you take it in CST and you turn it in. The quiz will focus on anatomy and physiology of the heart. Your coloring book assignments are things that I look at when I design the quiz, as well as the PowerPoints from this week. So do the coloring assignments, and you're well prepared for the quiz. Review the physiology that we talk about in class today and Thursday, and you're well prepared for the quiz.
This is going to be mostly anatomy, or?
No, it's going to be about half and half. Maybe a little bit more anatomy, but it's not. So those of you who took A&P1, the quizzes were mostly anatomy and the exams were mostly physiology. It's more mixed in this course. Okay, so let's go through. So are we in a pacemaker cell now? No, we're in a myocyte. We're in a contractile cell, either in the atria or in the ventricles. The mechanisms are the same. So this is a contractile cell. Does the cell depolarize spontaneously? No. The cell has a very stable, very negative resting membrane. Why is it so stable and so negative? You tell me. Why would these cells, ventricular myocytes, have a very stable, very negative resting membrane structure? They express a lot of resting potassium channels. Okay, so the cells are at rest. And they would stay at rest until they got stimulated to fire an action potential. What stimulates this cell to fire an action potential? Just your generic ventricular myocyte. What stimulated this cell to fire an action potential, which is about to happen? Before that.
Another action potential complex.
An action action potential propagates from what? A neighboring cell. The word I was looking for was neighboring cell, but that's right. An action potential happened in a neighboring cell. So this cell got a small depolarization from its neighbor. What triggered the neighbor? Its neighbor. What triggered its neighbor? The neighbor. We're going backwards up until we get to a pacemaker cell, right? So the pacemaker cells control the whole heart because the whole heart is connected to each other. But when we talk about this cell, its neighbor caused a small depolarization. Now, Cairo, what happened? Voltage-gated sodium channels open. Voltage-gated sodium channels open, and we get a fast depolarization because we have a lot of them. This is just like in the nerve that we talked about in cell tips and A1. What happens to sodium channels? Well, it's right there. What happens to sodium channels after they activate? They inactivate. So the sodium channels go into the inactivated state, and this large depolarization opens calcium channels. So sodium channels inactivate, and calcium channels activate. The calcium channels are slow, so they stay open for a long time. And so we have a long time of calcium influx. This is, 0.3 of a second, 300 milliseconds. Sort of, on average. So calcium flows in. What's that going to do to this contractile cell? Going back to the story at the beginning of this class. It's going to trigger contraction. It's going to trigger calcium-induced calcium release. It's going to trigger more calcium. Calcium is going to do its thing with troponin, contraction. So this calcium, this influx of calcium, is the trigger for contraction. It also maintains a long depolarization because the calcium is flowing in and flowing in and flowing in. Long depolarization. This long depolarization also opens voltage-gated potassium channels. And eventually, enough calcium channels inactivate and enough voltage-gated potassium channels open or activate and open, and the membrane potential repolarizes. And it repolarizes down to the resting membrane potential because we've got a lot of those resting potassium channels. So the resting potassium channels are not the same as the voltage-gated potassium channels. Voltage-gated potassium channels are important for terminating the action potential, and resting potassium channels are important for holding the membrane potential negative at rest.
All of them voltage-gated?
Are all of them voltage-gated? Well, no. Resting potassium channels are not voltage-gated. The rest of them are. The remainder are. So voltage-gated sodium channels are voltage-gated. Voltage-gated calcium channels are voltage-gated. And voltage-gated potassium channels these are all voltage-gated, opened by depolarization. But the resting ones are not.
In the previous slide, the voltage-gated calcium channels contributed to depolarization, but in the current slide, how can calcium contribute to repolarization?
So you're saying in this slide, the voltage, there's no plateau, and in the next slide there is? Is that what you're getting at?
So it's over.
mean, there is a plateau of sorts here, it's just very short, and it has to do with the number of calcium channels. So here, the voltage-gated calcium channels are responsible for the depolarization. They're responsible for a small plateau, and then they inactivate, and potassium channels repolarize. Same story here, except that we have more calcium channels, but eventually they inactivate, and then eventually the voltage-gated potassium channels cause repolarization. So the story here and the story here are very similar. So knowing the names and the sequences of these channels and how they make the resting, how they make the pacemaker action potential, pacemaker activity, and how they make electrical activity in contractile cells is on the quiz. Yeah.
So for this one, does the calcium channels directly express?
They're happening at more or less the same time.
Oh.
So it's not one or the other, they're happening simultaneously. Okay, let's do a clicker. During the upstroke, that's the rapid depolarization of the action potential in muscle cells, myocytes, what ions are flowing? So, going backwards, we're here. That's what we're talking about. So, is A true? Is A a correct statement? Yes. Is B a correct statement? Never. If there were potassium channels open, which there are not very many of, potassium would be flowing from oh yeah, okay. I could make this work. So B is a possibly correct answer, but it isn't. Why is it not much? Because we haven't given, so the potassium channels that allow potassium to flow out have not yet activated. And the potassium channels that are responsible for the resting membrane potential have become blocked. So there's very little potassium flow during this phase. Voltage-gated potassium channels have not yet opened, and resting potassium channels have blocked. So B is not correct. Is C correct? Not yet. Calcium channels have not yet opened. And so calcium is not yet flowing out of the SR. So the best answer is A alone. You could explain why there could be a little bit of B, and I would understand. Okay? When action potentials spread from one cell to the next cell, what ion flows are happening, are important? So we're going from one cell to the next cell. Which of these are happening? I'll give you a hint, it's more than one in this case. one's tricky. This one's hard. So is A true? I saw a bunch of green A's, so some of you think it is. Somebody explain it. I think it is. Now, tell me. Gap junctions are open. What's the most abundant ion inside cells? Potassium. So if one cell has a lot of potassium and it's depolarized, and the next cell has a lot of potassium and it's not yet depolarized, potassium is going to flow from one cell to the next, right? So if this is cell 1 and this is cell 2, and this has a lot of potassium and this has a lot of potassium, and we put a bunch of holes, pores, gap junctions there, and we make this cell positive relative to this cell, we're going to move potassium from cell 1 to cell 2. So A is definitely true. Is B true? Zoe, why not? I'm sorry, Lauren, why not?
Because aren't the channels inactive?
But so sodium channels, voltage-gated sodium channels aren't they're not the only way sodium can flow. What flows through gap junctions? Pretty much anything that's small, including sodium. So is the sodium concentration inside cell 0? No, it's low. But the same force is going to push sodium from one cell to the next. So B is also true. Is sodium flowing from outside to inside in both cells? Well, it depends on how much depolarization has happened. So this cell has depolarized a lot. And this cell has depolarized a little. Is sodium flowing in to this cell? That's what we're asking. Sodium flow from outside to inside. Yes, through voltage-gated sodium channels because it is depolarized. Is the same thing true here? More or less. So yes, you could argue no if you say, okay, this cell is so depolarized that the sodium channels have inactivated. Okay, I understand where the no is coming from. If you say this cell hasn't depolarized enough so the voltage-gated sodium channels are not yet open, then I could understand why you would say no here. But there is certainly a way that both of them could have sodium flowing in if they have both acquired an action potential because they've both reached threshold. Is D a true statement? D is never a true statement because potassium never flows inward through channels. It's always pumped inward through pumps, but it never flows inward through channels. It never happens biologically. So A, B, and C are acceptable. You see why A is definitely correct. B and C you could make arguments here. Questions about this?
So by flow, you mean like they're traveling downhill?
Yeah, flow is down. Flow through channels is always downhill. That's a key thing to know. If you start to pump ions through a channel, you've got a problem. That's not what channels do. Okay, so this is just to remind you that the calcium influx through the calcium channels is what triggers contraction. We'll talk about refractoriness in a minute, on Thursday. But the point of this slide is that the electrical activity of channels and the calcium influx through those channels is what triggers contractile force. And electrical activity is fast and contraction is slow. Okay? So the green line is the electrical potential And the red line is the pressure or the force or the contraction. And calcium triggers contraction. Okay, so let's do another clicker. During the plateau, when calcium flows into the cardiac myocyte from the extracellular space, so during the plateau, when calcium flows into the cell, how does it trigger contraction of the myocyte? There's one best answer, but there's two correct answers. The best answer is D, because D says then go to B. Okay? B is a true statement. But B by itself isn't as correct as D by itself. D and then B is the correct answer. Okay, is that clear? So let's walk through the heartbeat now from an electrical perspective. Hopefully you know a lot more about the heartbeat than you knew, an hour and 15 minutes ago. So we start at diastole. The heart is at rest. It is refilling with blood because the pressure in the body is bringing blood back to the heart. And the blood pressure in the lungs is bringing blood back to the heart. SA node depolarizes by the ion channel mechanisms that you now understand, or will understand when you work through it. SA node fires action potentials by the mechanisms that you now understand. Calcium channel dependent action potentials. Those action potentials spread throughout the atria because of gap junctions. The contractile cells in the atria contract, and we get atrial systole. The action potentials spread through the AV node slowly. We'll talk about slow conduction probably on Thursday. This causes the delay. The slow conduction in the AV node causes the delay between atrial systole and fast conduction in the bundles, bundle of His, bundle branches, Purkinje fibers, ventricular muscle, now ventricular systole, by the mechanisms that we've talked about, the calcium channels and the sodium channels that we've talked about. Then, okay, so now, after, I'm going to go back. So after the action potential and the plateau has spread throughout the ventricles, well, first throughout the atria, then throughout the ventricles, causing contraction, first in the atria, then in the ventricles, then there is a wave or a spread of repolarization. Repolarization. So the depolarization spreads, and then the repolarization spreads. And the heart relaxes, and we do it over and over again. So I'll start on Thursday with the mechanisms for the slow, delayed depolarization in the AV node. And we'll build more knowledge from that. That's it for today.